escucho gente, voz de fondo. No sé si eres tú o son otros que estén. Mira, pone live.
Otro, yo creo.
Vale.
Como la asignatura de trabajo de máster, pues no.
Anda. Uf. Vaya. Tengo que salir y vuelvo a entrar. Temas de permisos para compartir pantalla. Me uno ahora.
Ok.
Presentar y hacer una prueba de animación. Entonces, contestó la niña,
Are you here, Day?
Yes, I just joined again.
Okay, great.
Yeah,
I
hopefully
think
this time I'll be able to share the screen.
yeah, not only that, it's already recording, so that's fine.
Okay. How about now? You should be seeing my screen, are you?
Yes.
Excellent. So, all set, apparently.
Yes, let's wait for 5 minutes or
Sure.
we start. Okay, I think we can start. Can you hear me, at least you, Hodei?
Yes, I can hear you. I hope everyone hears me as well.
I do. So, and you see me too? Yeah.
Yeah.
Well, so welcome everyone to the first seminar of the new seminar series on AI for space. Before introducing our first speaker of this series, let me introduce a little bit the motivation and the supporters, the sponsors of this series. So this is, I don't know if you see my background, there are like different badges, basically representing who we are. And this is an idea that came from Professor Massimiliano Basile, who I think he's here. Yeah, I think he is. And I, who are leading the IEEE task force on emerging technologies in aerospace science and engineering. And as part of this, we will organize different activities. And one of these is this new monthly seminar series in the intersection of AI and space that, as you know, is being booming for quite a bit right now. And we hope to bring here the latest and greatest advances in research and in transfer to business and everything that is around this topic. I don't know, Max, if you want to add another comment, but let me, so this is the logo that you see on the bottom of my background, is IEEE. Then my name is Victor Rodríguez Fernández, and I'm a associate professor at Universidad Politécnica de Madrid. And then the other two badges correspond to the institute that Max leads. I don't know if, Max, you can unmute and talk more about it. If you want to introduce the institute, I cannot activate it. Let me introduce the microphone. Thank you, Max. Because here it is. Hello, camera. Hello, mic. Can you speak now, Max? No. Yeah, I think so.
Hi.
Yes.
Hi,
yes.
Victor. Thank you very much for the introduction. Unfortunately, I couldn't, use the microphone or the camera, so I don't know.
No, I think I had to enable it to you. Sorry, this is the first time, but it will be smoother in the future. If you want to make a mention about your institutions and the institute.
Yeah. First of all, thank you very much for organizing this seminar series, and welcome everyone who is attending today. As Victor said, my name is Max Basile. I'm the director of the Aerospace Centre of Excellence at the University of Strathclyde in Glasgow, Scotland. And thanks to the support of the UK Space Agency, a couple of years ago, we created an institute on AI for space sustainability together with people at the University of Arizona, Professor Furfaro, people at MIT, Professor Linares, and then people in Canada, a company called Columbiad, and the University of Waterloo, Professor Nasser, and also people in the UK. We had the Alan Turing part of the project, some companies like Lift Me Off, and then also people in Australia. So we had also partners, Nominal Systems in Australia. And from there, we had the idea of doing more AI connected to space. And I've been collaborating with Victor for many years on the use of AI. And since both of us are part of this task force that started actually in 2014, so very, very long ago, we thought, why
Before
not?
AI was cool.
Yeah. Why not creating a seminar series that everyone can enjoy with very knowledgeable people like Hodei, who's here today. So I don't want to add anything else. Please go ahead. There is a better speaker for today. So
thank you, Max. Thank you so much, because I'm not going to claim that for me. It was originally his idea. I have to say that. And if you allow me, can I introduce the first speaker today? Yeah, so the first speaker is Professor Hodei Urrutxua. He is an associate professor in aerospace engineering at Universidad Rey Juan Carlos in Madrid, and he's also the co-director of the Spacecraft Proximity Operations Laboratory, SPOL lab at URJC and the same university, a robotic testbed intended for the development and validation of optical visual navigation and guidance algorithms for spacecraft proximity operations. Aside of that, he's a good friend of mine. We've been colleagues for a while. We've been supervising some PhDs together, and we have ongoing projects here too. And I'm super happy and super excited that he's the first one inaugurating this series. So thank you so much. Let me tell to the participants and to the attendees that this is going to be recorded, and it will be uploaded afterwards to a YouTube channel that Max and I created for the task force as well. And please, all the questions that you have, you can start writing them in the chat, and before the end of the webinar, we'll have some time for a Q&A. Okay, so the floor is yours today. Thank you so much and welcome.
Thank you very much. Also, thank you, Victor and Max, for considering me for this first talk of the series. I hope to meet the expectations you were putting on me. And yeah, basically, I'm going to be talking about kind of an intersection between the astrodynamics world that I've been doing research on for quite some years now, and the AI that I'm slowly getting deeper and deeper into. And yeah, it's going to be an overview of many research lines that we have ongoing with collaborators, PhD students, and so forth. So it's going to be quite general, and I hope everyone can get something new, something interesting from this talk. I'm going to talk basically about these 4 points. Let's get started with the introduction to give some background of where we are and where we believe we'll be heading to in the next decades. Well, currently we are accustomed to going back and forth from the Earth to the space station, and technology has evolved so much that now everything's done autonomously and with a high degree of automation, where astronauts now don't even need to do anything but sit on their chairs and wait for the spacecraft to do everything. And well, as a paradigm of the most complicated, probably, space operations we can think of in Earth orbit, we find active debris removal. So this is putting the most challenging demands on the guidance, navigation, and control subsystems for a spacecraft. So this is kind of the holy grail we hope to strive towards in the next years. And we also hope to make it even more difficult than that. Now, well, for a few years now, Moon is gaining attraction again, not only by space agencies, but many private corporations that are actually the ones probably pushing harder. The difference with past times in history is that now it seems that we are planning to go there to stay, because we have some business, some profit to make on the Moon, or that's the idea at least. And this will put us in a very different paradigm than what we've been before in history. We will be needing to take supplies, resources, crew from the Earth to the Moon and back. Eventually, we'll hopefully be going to deep space as well, to Mars, to other places, and all this needs to be running smoothly, kind of like a subway network can take us anywhere in a city. We will need some network of space transportation that can take us back and forth and get everything running. So this is going to be a lot of spacecraft, and we cannot rely on old technology like when we got to the Moon, that everything was done mostly by hand. So astronauts were doing everything manually. It was clearly human in the loop and with a very low degree of automation. So totally different from the stage we're at in Earth orbit. So this degree of automation, we need to take it to cislunar space. And these proximity operations like rendezvous, in orbit resupply, maybe in orbit assembly of space structures, it will need to be done routinely and above all safely, because if astronauts are going to be involved, then safety first is going to be a must. And there's some good reasons for which we will need all of this to be done autonomously. One of them is we cannot rely on ground communications if we are on the far side of the moon, because there is no direct line of sight communication. And even if there were, we have a light time round trip of 2.5 seconds. This means that some critical operations cannot be done in real time if we are depending on ground communication. So we need to do this autonomously. So we cannot rely on ground. And this gets even worse if we are considering as a proxy to proximity operations, not just proximity in between spacecraft, but proximity to terrain or to lunar surface. It might seem something that we should already know how to do, but if you take the numbers, only in the past 25 years, half of the missions to the moon that attempted to land on the moon have failed. Most of them actually with a hard impact. They crashed literally. So it's hard. And it's hard mostly because everything needs to be done autonomously. So there's still many challenges that need to be solved. And if we think ahead into the future, it's not just the moon, but deep space. So not only Mars, but asteroids that we will be hopefully visiting within our lifetime. I really hope so. So we will be considering stuff like asteroid mining, and many of these things, they will not be done by humans, by astronauts. They will be done by robots, and these robots will need to make decisions on their own. We will just send them with some clear mission priorities that they will need to follow, but take decisions on their own with minimal input from the ground. Even more than that, there's also another shift in the way we do things. So far, we've been sending basically single individual spacecraft to asteroids and other planets, but now things are getting more complicated. We are sending not one, but many spacecraft, one at a time. And this is going to keep getting more popular. So we can think of systems where there's a big mothership taking control of a swarm of smaller, more specialized spacecraft, performing very specialized tasks. And all of these would need to be coordinated somehow. And everything done basically on their own, without human intervention in the loop. So we can identify, coming back to cislunar space, a set of challenges that are of paramount importance that we need to be able to solve reliably. We could think of relative pose estimation of co-orbiting spacecraft. We can think of characterization of the spacecraft itself in shape, texture, different elements of the spacecraft. We'll talk about that later. Spacecraft synthesis or shape and texture reconstruction. We may need to consider collision avoidance for safety and robustness issues. We will need to be doing station keeping maneuvers in complex dynamical environments. We may need to also compute low thrust orbital transfers in between departure and destination orbits, maneuver scheduling, 6-degree of freedom trajectory planning. This is challenging as well. Optimal onboard control and guidance, also automation of ground station operations to lessen the workload of people on ground, and everything would need to be tested and validated in a full systems verification fashion. And it is around these objectives that we conceived this research project that just kicked off barely a month ago, this September, divided in two sub-projects. Juan Luis and myself are IPs of one sub-project, and Victor and David are coordinating the other sub-project. And we hope to be facing, trying to address all these challenges. So, features of GNC algorithms that need to satisfy these demands for cislunar operations. First and foremost, they need to be autonomous. They need to be run on board. They need to be efficient because they need to run on computers with limited computing capabilities, limited memory footprint, and so on. They need to be robust. They need to work out even if things we encounter are not as we hoped or we expected it would be, and they need to be able to react to the uncertain. And they need to be safe. So these systems cannot fail. And on top of that, we think there should be another layer of we can think of intelligence, like something taking care or orchestrating everything else. And this is where many AI-related services come in. We can think of autonomous agents playing a significant role here. Techniques like image segmentation, 3D image synthesis, foundation models we believe are going to be of paramount importance, and well, along etc. So we structure our project in a set of work packages, and I'm going to be basically discussing in this presentation more in detail things we've done or we are planning to do on work packages 2, 3, and 4. So we're going to organize them around a first section on guidance and control, another section of optical navigation, and a last section of training data. Let's start with guidance and control. Those of you who love science fiction, you've encountered many times situations where the captain of starship asks the computer to plot a course to somewhere, and the computer takes care of everything. It tracks a trajectory that's safe, that avoids hazards or obstacles. By the way, Picard never asked to plot a course to the onboard computer. It was always to another people on the cabin. We can think this. We can think of this as evolving into more complex human to computer interactions, where we can ask the computer to consider multiple options, to not only plot courses, but make them optimized for maybe more than one spacecraft. But all of that so far would be somehow managed by a human in the loop, taking the decisions and asking what they want the computer to do. Next step or next evolution of this would be, of course, considering that we give this smart system agency to control the whole spacecraft, regardless of any human. Example, we need to send, I don't know, colonists outside the galaxy, hibernating. The spacecraft would need to take care of everything during decades. Okay, so that's like the far end of the road we are walking towards. At this moment, we've already encountered a few software specialized for design of orbits that automatize a lot of things. They do include many AI elements, but still the flow is driven by humans. Humans are in charge of what they want to do for what they want to achieve for their mission design. Okay, these will get increasingly more complicated because we will also need to include the computation of low thrust trajectories. That basically implies solving optimal control problems that are very hard and computationally demanding to solve. And AI is still finding ways to conveniently solve that within reasonable computational load. But we are already putting more and more ingredients, more and more building blocks that will enable us in the future to embed many specialized AIs around an agentic workflow and eventually let it do everything by itself with just a human telling, consider a mission for doing this and that, and they will take care of all the mission design, the mission scenarios, and so on. At the moment, we are trying to struggle with more efficient ways to compute these optimal control problems for low thrust trajectories. And there's techniques that can actually give us an approximate, but usually sufficiently good solution that takes only a fraction of the time. And this is probably the first step towards enabling an AI agent to consider multiple mission scenarios and and deal different mission configurations, different trajectories, and so on. But AI is also already getting into the way we can compute these low thrust trajectories. There's an interesting paper in 2021 where they did use reinforcement learning for a QLOW approach for designing LEO to GEO transfers. And it was a very interesting paper. I love the idea, the approach. And recently we've been working on an extension of this work, and we have more extensions in mind. But this extension managed to basically include the attitude dynamics part as well, and the power constraints. So it keeps bridging the gap towards an operational environment where one such algorithm could be embedded on board and compute orbits on its own very efficiently. We'll be presenting this in IAC, or maybe we already have. No, I think it's in a few days. So we're working in this direction because reinforcement learning has many interesting avenues, and I think we'll keep seeing it more and more in the future. Not only we will need to take care of designing transfers and maneuvers to go from one orbit to another, but we will also need to go from wherever we are to the neighborhood of a given spacecraft and try to dock, to rendezvous and dock with it. So far-range rendezvous is not very different from an orbital transfer, so we can still use the same set of techniques. But the closer we get, then we start seeing different situations where perhaps AI can help us with. When we are in the close-range rendezvous, especially if we are going to make rendezvous with, I don't know, a space station with large solar arrays, there's some elements that we simply cannot crash against. So when safety issues come into place, we may need to consider trajectories that we need to compute on the fly as we are approaching it, because some uncertain things can happen, like unexpected maneuvers, or you identify a risk and need to perform a collision avoidance maneuvers. So for plotting these kind of trajectories, we believe that AI-based techniques for path planning are going to give us an edge that will allow us to perform this faster and reliably on board. There's already missions around the Earth trying to solve the 6 degree of freedom rototranslational problem for docking with uncooperative objects. This is very challenging. So this is where the eyes of the community are put on. And not only you need to move the spacecraft around, but also rotate it in a way that you synchronize the relative movements with respect to the target. You need to cancel it out so you get a successful docking. So really very challenging. Similar for berthing, where you don't need to move the whole spacecraft, but you still try to use a robotic arm, perhaps to grab the target object. The post-capture phase is kind of tricky because both spacecraft start moving around, so that also needs to be taken into account to know how we approach the target. So these are situations where we are investigating ways to incorporate techniques supported by AI to solve these challenges. I'm going to talk more extensively about the optical navigation part because that's where we are. Well, that's where we are trying to put most of our research time and research resources in our research group currently. So, as an introduction, the classical way of classifying a target spacecraft is following two distinct categories. On the one side, we can consider whether it is active or inactive. Basically, if the target is active, it means that it can hopefully control itself or do maneuvers, or at the very least, it can communicate and give some information or feedback to the chaser object. When the spacecraft is passive, we cannot expect it to do anything to help us perform the eventual docking with it. Then there is another classification where we can consider the target to be cooperative. Basically, if it is cooperative, it means that either it has some sensors that help us do the relative pose estimation. There may be some data link established between the target and chaser spacecraft. The target may have a purposefully built docking port, and it can maybe even perform maneuvers to make our life easier for the docking. And the most restrictive situation would be when it is not cooperative. So basically, the target spacecraft needs to do everything on its own. And these two classifications can be combined to give rise to different situations. For example, if we consider the target to be active and cooperative, this is the easiest part. This is what we encounter for the Crew Dragon capsule, the ATV. So anything going to the ISS currently is under this situation. The ISS is active and is cooperative. Life extension missions that have been successfully accomplished would also fall into this category. Other situations we might encounter. The spacecraft might be active, but still uncooperative. So the spacecraft can do things, but it will not do anything to help us do the in-orbit inspection or berthing or docking or anything. A typical example of this would be military espionage kind of use, where with satellite you try to inspect someone else's satellite. We might think of other situations where perhaps a rescue mission may need to be performed, as in the 2010 movie based on the book with the same title. It's the follow-up of 2001, very interesting movie if you haven't seen it. Also closely related to AI, it kind of explains why HAL 9000 did what it did in the original movie. Then, if we suppose the target is passive but cooperative, this can be accomplished if the target has, for example, built-in retroreflectors, or it has docking ports, or it has some kind of markers that will facilitate the in-orbit proximity operations with the chaser. And the most challenging of the combinations would be passive and uncooperative. Since this is the most challenging, this is the one we should probably try to address. For two reasons. One, if our target is passive and uncooperative, as for an active debris removal mission, we need to go for this. But even if the mission were passive or cooperative, we could still use the techniques for this combination as to support and to have redundancy on our systems. So where can AI be most helpful of all of these four approaches? Well, basically when target is either uncooperative or passive. So in these three blocks, we believe AI can contribute. So we'll see in the following slides what specific tasks AI has proven to be worthy to make an impact in these technologies. For example, when we have an uncooperative target, there's a series of assumptions that are usually made, and these assumptions do not necessarily need to comply always. One of them is that we know the geometry of the target spacecraft in advance. We assume this because we usually want to go to specific spacecraft for one reason, so we know where that spacecraft is and what it looks like. And we may also know what are some relevant or meaningful features or key points or landmarks on that spacecraft. Now, the problem is that these assumptions do not necessarily hold. For example, suppose you get to your target spacecraft and suddenly the geometry is not what you expected. It's got some damage, some micrometeoroid impacts, like basically something that rendered your pre-built model of the target spacecraft unusable because the geometry is no longer what you trained your GNC algorithms for. Or for the same reason, suddenly some of the key points you were hoping to have available are no longer there or are not defined. So these are challenges that we have to think ahead and try to solve. With all this in mind, we might encounter a very simple application for target detection and segmentation. For example, whenever we get close to a spacecraft, we want to do something with either docking or inspection or whatever. It is interesting to be able to identify different parts or components of the spacecraft. For example, from my picture, what exactly belongs to solar array? What is the orientation of the solar array? That might give us information on first where it is. Let's try to plot a path planning, a trajectory that prevents collision with the solar arrays or appendages or antennas. So very valuable information, both from safety considerations and from target spacecraft integrity check purposes. There is a very nice and interesting paper, 2022, where they tried some segmentation algorithms available at the time on spacecraft, and they performed pretty nicely. They tried this for various geometries of spacecraft, and the success rate in identifying different elements is very high. So very convenient and actually very easy to get with current technology. As it turns out, at the moment, I had an ongoing PhD student that had already been working on experimenting with image segmentations for trying to separate, for example, solar arrays from the body of a spacecraft. He did use this algorithm, MASC-R CNN. He only tried it for a more limited data set, and he didn't do such an extensive job as the ones in the paper I presented in the previous slide. But it was about that time of just a few months around the same moment. So there was some interest already at the moment. My PhD student Ben did try it for different satellite geometries, and results would generalize relatively nicely, although you can see there's some occasions for which it didn't perform too well. Still, technology has evolved, and we have increasingly more capable models. Actually, this morning, as I was finishing to prepare this presentation, I just passed on a random image of a spacecraft to segment anything. Victor is laughing because he told me about this model already a year ago, and I didn't test it myself until this very morning. And just with the base model, without specific fine tuning for satellite imagery, it very easily recognizes solar arrays and other elements. It can even do cutouts of individual objects. So it performs very nicely. And as I was coming, driving to the office for this talk, I was also talking to ChatGPT, who would let me know that there's many versions, many variants of this model that are intended for a specific task, either fine-tuned, quantized, made faster. So there's versions that you can run on a mobile device, on a handheld device. So very appropriate for edge computing. So we could ideally bring one of those on board the spacecraft. And the trade-off between the performance of the model and the computational resources is about finding a sweet spot. So how much can we bring on board? But very promising, and it's already something that is ready to test in space and to take for granted we can have for more complex systems for application in cislunar environment. So coming back to the case where we can consider the spacecraft integrity to have been compromised. So this will be problematic for navigation algorithms that may have been pre-trained on the real object or a model of the real object. So this will require an in situ modeling of the actual geometry that we encounter. So for that, we will require some techniques for spacecraft synthesis, which is reconstruction, in situ reconstruction of the shape and ideally also the texture of these spacecrafts. We can also turn around these two ideas. Suppose we have a preloaded model of the spacecraft, then we go to the vicinity of the spacecraft. We build an in situ model with a synthesis, spacecraft synthesis model, and that allows us to compare those two models. And maybe there's no broken solar array or any missing part, but by direct comparison and, for example, looking at the textures, we might get some interesting notion about, for example, the degradation of the surface material properties that might give us information on perhaps how well materials are holding, how reliable they are if I want to grab a specific part of the target spacecraft with a robot arm, or how it has how the space environment has affected different parts of the spacecraft. So we could get useful information that can be fed into the GNC algorithms, so we can take informed decisions on board based on that additional information. There's many ways for trying to take a picture or many pictures and try to get a 3D model that we can use. First time I heard about this, again, when Victor told me about this, the trendy thing were the NERF models. And they've already been tested for space applications with more or less success. But these models have basically, they have blossomed in recent years. So the number of available models and their capabilities has skyrocketed, and there's many different techniques that improve on mainly use of computational resources. And well, it's hard to catch up because new models are released every few weeks. And again, this morning I found that this paper already a few months old, where for different situations, different original pictures, they try to apply different techniques for reconstructing the spacecraft. And what we can see is that if we remove all the background noise, so there's no laboratory elements like walls, curtains, or anything. So if we remove the background successfully, all of these perform pretty nicely. And 3D Gaussian splatting is actually very, very efficient, much more efficient and resource demanding compared to NERF. So it is, again, technology that seems already not only suitable, but kind of ready for in-space demonstration, as long as we can have some adequate hardware to run these models on. But for low Earth orbit, it's very much doable. Now, another application many people overlook or don't even consider when we talk about proximity operations. First thing that comes to our mind is close range. So few meters away, few tens of meters away from the target spacecraft, where we can take a nice picture, where we can see the pose of the object. We can apply the algorithms we described in previous slides. But what people, as far as I know, are not really looking at is what happens when we are further away. Like, consider a few hundreds of meters away. The target spacecraft may typically be so far away that we cannot recognize its rotational state where it's pointing. But the further away we move, the more it becomes a point mass for us. So it will become a luminous point of light in our sensors. So basically, by staring at it as we close in, we can get light curves. And light curve inversion is a well-established technique for telescopes looking at space, and it allows us to get information of its rotation axis. And if we have more information on the actual target spacecraft, like what its geometry looks like, we could even get information of the time series of its rotational state, like what is its attitude as a function of time. So it's a way of getting us information ahead of time before we get to the close range proximity operations. Okay, so this all adds up to the things we can use to feed our GNC systems. Now, a very typical challenge in proximity operations in co-orbital motion is that of relative pose estimation. It's of paramount importance for the case where target is passive and uncooperative. It is so important that there's been several challenges for relative pose estimation, but it's a technology that for many has already accomplished a certain degree of maturity. So if we have a detailed model for the target spacecraft, we can fine-tune a relative pose estimation algorithm based on AI techniques that can perform very well. Problems come when we don't have a very good model of the target, or we want a model that can generalize to targets that are unseen in the training data set. We can again be looking into the far future and consider that maybe 100 years from now, there will be as many different types of spacecrafts that algorithms would need to be kind of agnostic to individual models of spacecraft, but be more general or more capable. So the typical pose determination pipeline based on feature extraction is composed of these three elements. First, we have a feature extraction. then we have a feature matching element, and then we have geometric pose estimation. For feature extraction, there's two subtasks that need to be accomplished sequentially. First, we need to detect the features on an image. Second, we need to add some descriptors to each of those features, so we can later track the evolution of those features as a function of time as we get a series of images. Now, for feature extraction, there's a plethora of methods based on classical methods. Basically, they are computer-based, computer vision methods that rely on identifying points, edges, vertices. So it's a very mature technology. It's efficient and robust. And on the other side, we have some AI-based methods that have been taken over because they offer some potentially some interesting improvement in the capabilities, and they can outperform classical methods. Then for the feature matching algorithm, we also have that dichotomy where we can choose between a classical method, typically based on nearest neighbor or similar methods, or we have AI-based methods that that we can consider. And for the geometric pose estimation, there is usually little incentive in trying to approach this with AI because it's there's well-established techniques because it's an algebraic problem eventually and an optimization problem. So we rely on classical techniques usually. Now, there is often another block we put ahead or before the geometric pose estimation, which is an outlier rejection block. Typical choice would be ransack, but not necessarily. Now, we might also consider, before feeding the image to this relative pose estimation, often we need to recognize where exactly within that image is the target spacecraft we are interested in. So this often requires some region of interest segmentation. Again, AI can do this very, very nicely and very easily. And often we might need yet another pre-processing step where we try to remove the background. For example, we don't want any stars in the background, or if we have the Earth or the Moon on the background, we also want to remove that to reduce noise and hopefully improve the performance of these techniques. Again, this can be done with classical techniques relatively nicely and easily. There's no much overhead to the pipeline. Now, coming back to the PhD student I had back in 2022, he did try to explore trying to include a feature extraction algorithm based on CNN, convolutional neural networks. He proposed an architecture that was able to deliver key points from a picture without knowing what points of the picture were a priori better or worse. So he trained the network so the network would figure out which points may be more useful for later downstream tasks such as feature matching and geometric pose estimation. So this is an example where we get the input image and we get as an output a set of features or key points. It may seem kind of randomly distributed, but would we take different key points and it wouldn't perform as well as it did. So there was some optimization involved. Then he took that network and for feature matching, he doubled that network to get a Siamese structure. And to that output, he added another set of layers. So the feature matching would also be done with AI. Okay. And we could get, as you can see in these results, a clear benefit compared to classical based methods for relative pose estimation. And these methods got even better when we introduced ransack algorithm. So for this validation set, we actually got below 1 degree error, rotational errors for the pose determination. Very interestingly, this algorithm was so generic that we even tried, despite it was trained with only spacecraft in the data set, we tried to provide images that were not spacecraft, and the feature extraction performed still comparably well. So he managed to get some kind of universal behavior or some very nice generalization. And this may be interesting if, in case we find some target spacecraft that do not have the expected geometry. It's a nice feature to have. Another interesting work performed later by Miguel. I saw you were in the seminar. So I'm going to discuss a little bit the main takeaways of the work he did for his masters. He tried to replace these 3 blocks: region of interest segmentation, feature extraction, and feature matching, using the YOLO algorithm. YOLO can handle also background relatively nicely, so without much penalty, we can skip that pre-processing part. And he managed to implement, to fine-tune this YOLO model for a data set based on the Deimos 1 spacecraft that he himself developed. We'll talk about that later. The model worked quite nicely once able to return as an output both a bounding box and a set of reference key points that we can then pass on to a perspective endpoint algorithm. And he got some very nice performance metrics. Very low translational errors, just a few centimeters of positional error, and about 2 to 4 degrees of error in rotational accuracy. We've later done some experiments trying to apply not even some fancy filtering techniques like extended Kalman or anything, but by doing a very simple smoothing technique like people do for stock market analysis. We found that it's relatively easy to lower this by at least 1 degree, if not divided by a factor of 2 in many cases. So performance are kind of nice. Later on, we continued the work started by Miguel and with another PhD student we have at the moment with Luis. We try to also repeat the whole thing for the same data set with NVIDIA's center pose algorithm. It's also based on feature extraction, but it has a very interesting feature. It basically allows you to choose which feature extraction model you want to use, either a CNN-based model or another model, the FAN model, very similar to a transformer architecture. We are still getting the results for the transformer architecture, but we hope that it should offer some benefits compared to convolutional neural networks. And now it is interesting to note that center pose requires, if you train or fine-tune the model for one single spacecraft, it just needs the image, the picture. But if you try to use this for a spacecraft that was not in the training data set, then the model also requires you to load some representation, basically a model of a 3D model of the spacecraft. So again, this is where spacecraft synthesis might nicely bridge the the gaps that we have in the pipeline in case we were to encounter a spacecraft that had some damage or some change in the expected 3D model. Results he got were very were very nice and comparable in performance to the ones we got with YOLO. Going back to the training data, it is interesting to know that all these AI-based techniques, they need some data sets to work on. And in orbit, real imagery is very hard to get. Typically, unless you have a satellite of your own flying, you are not going to get anyone to give you real in-orbit imagery. So, for example, these guys, they had to spacecraft co-orbiting, so they were building their own data set. Everyone else we need to figure out by ourselves, and we often have to go for computer rendered data sets of images. My student Ben also had to develop his own framework based in Blender 2 for developing data sets that he could then use for training his relative pose estimation algorithm. It had some labels that allowed, for example, the image segmentation approach. If anyone had interest, both the computer framework and the whole data sets are freely available on the internet in the GitHub or Kaggle websites, respectively. Then Miguel also had to develop his own data set. This data set was specifically dedicated to the Deimos 1 spacecraft for reasons related to our previous research project. And as annotations, it includes bounding box and reference key points. These key points for the spacecraft were manually picked. So Miguel picked key points he considered that were appropriate, and the data set includes them. This framework was built for Blender 3, so that allows the new rendering engine that does ray tracing, includes like a lot of features that provide better quality images. So the quality is quite stunning. So it's a very good data set for training our algorithms, and we're using it currently. The algorithm considers different configurations for the viewing angle, the illumination angle, and the distances in between target and target spacecraft and chaser spacecraft. But we realized that, for example, the distribution were not uniform, but instead they were uniform in longitude and latitude. But when you convert that to 3D positions, it comes with some clustering around the poles. So that introduces a bias in the data set. We can see that in the distribution of positions of the object in the data set, where we can see some peaks in the distribution around the poles. So we think that correcting this should improve the quality and the uniformity of the data set. And that's what we are working on with Luis at the moment. So we are extending the data set that Miguel did using his computer rendering framework to add two improvements. First is to get a uniform distribution of points, so we can try to smooth this distribution so it remains kind of uniform as it is expected. And the other is trying to add one more annotation to the data set, which is the visibility of the points, because we realized playing with YOLO that for training, YOLO can use the visibility of the points. And when you make an inference with YOLO, it can also tell you whether each of the key points is or not visible. And preliminary results we got suggest that if we only use key points that are visible for the perspective endpoint, geometric determination, the performance of the algorithm is better. It improves the performance. The logic behind that might be that the key points that are not directly visible in the image, maybe YOLO is not capturing them as precisely as it is capturing the key points that are actually visible. So we are working in improving these two aspects. The next level of quality improvement for these models is the laboratory imagery. So instead of rendering the images, we can make mock-ups of the satellite, make them have textures alike the real spacecraft, and we can take pictures in a robotic environment, in a robotic testbed, like this one, with appropriate illumination conditions. There's many of these testbeds around the world. This is the one they have at ESA. In Germany, at DLR, they also have the EPOS 2. This is a larger setup that allows to test real size, like one-to-one scale, potentially models with the benefits it has. We'll talk about that later. Northrop Grumman, for the life extension vehicle, they had to build their own set for testing their algorithms with the actual spacecraft, with engineering models of the actual spacecraft. For this laboratory imagery, there is some important considerations regarding to lighting on the one side. So we have light boxes to simulate the Earth albedo. We have sun lamps to simulate sun. And what advantages have, apart from realism, this laboratory imagery as compared to, for example, computer rendered? One of them is the stray lights that we can encounter. Stray lights occur when we have optics, real actual optics in our camera. They occur naturally under certain conditions. For example, we have glares, we have lens flares. They use them a lot in the new Star Trek movies. They look very cool. We have veiling glares. So there's different kinds of stray lights. The problem is we should be able to reproduce them in a laboratory environment because we are using real cameras with realistic lighting. But for computer rendered scenarios, it is harder to get. There's software for getting them, but they need manual intervention, and you need to tell where to put a lens flare or a glare, for example. So since it doesn't show up realistically, it is not as realistic as we would encounter in the space. So there's a catch. Also, there's manual process involved. So you would do that for doing the visual effects for a movie, but not for a data set of thousands of images for training a computer model. Light is very important. When you go to one of these laboratory setups, you would like to reproduce daylight. And then you find out that depending on what technology of light bulb or lighting, the spectrum does not match that of the sun, of daylight. So current technology is based on LED, on LED. And instead of having per pixel 3 LEDs for 3 different colors, in order to try to match more reliably solar light, there's technologies that use up to 6 different LED colors. So when combined, the resulting light is closer to sunlight. This is important because depending what light you illuminate your spacecraft with, the colors and the tones will be affected. So if you want your data set to be more realistic or to more closely match what you would encounter in space, you need to take all these considerations into account. So there's a whole set of spotlight options that have, they have the correlated color temperature and color rendering index, CRI. CRI, the closer to 100, the closer it matches solar lights. Then I've been talking to benefits of laboratory imagery. What about the drawbacks? We also have drawbacks like we don't have the Earth on the background. How are we going to figure out how to put the image of the Earth on the background so we can get that in our data set? It can be done with some trickery. Either we cut out the spacecraft and overlay it to a computer rendered or to a real picture of the Earth from space, or smartly we can use chroma key composition technique. So we can basically put every light we want, anything we want around the spacecraft itself. More, and this is harder to get. What if the spacecraft is close to the horizon line? Then this is tricky. Okay, this is complicated to get. Now, other things we cannot get unless we have the real spacecraft with the real materials and illuminated with sunlight at the real flux, at the real incoming light intensity, we can match the resulting spectrum in the visible range, but we are not going to match it in the infrared. So we can use this for generating datasets in visual range, but if we want to make sensor fusion with infrared cameras, laboratory setups are going to be complicated unless we have basically a one-to-one scale laboratory environment. And this is how we get to the spacecraft proximity operations laboratory that we are building ourselves in-house at my university. So I'm going to briefly discuss without getting into too much detail because I don't want to be running late. I'm already running a few minutes late. So in 5 minutes, I'll be done. Basically, we have our own laboratory that we are building from scratch. We started from an empty room and try to build one that looks like this. Let's take a closer look to the different elements we have. On the one side, we have a couple of robot arms, 6 degrees of freedom, one for taking the camera, the optical sensor that would go on the chaser, another for replicating the rotational motion of the targets. We, of course, need a mock-up of the target. We need a linear system, a long rail to move the big robot arm along to simulate, to replicate an approximation corridor to the target spacecraft. We need convenient lighting equipment that can reliably simulate lighting conditions. Motion capture cameras, so we can track the rigid body position and orientation of the different elements within the laboratory. We also need some cameras. And yeah, this is it. So basically with our current setup, everything that has motion capture camera system markers attached to it, we can locate with positional errors of about 0.1 millimeters, so some millimeter accuracy. That's what the system can deliver. We actually can go slightly below what individual cameras can provide according to the manufacturer, and we know because we tested. And pointing accuracy depends on how far away you put the markers. So it depends on the actual size of the mock-up and the camera and so on. But again, about half of degree of accuracy with the current setup, and we can get lower. Calibration is complicated. It's been a real headache for several months already. It's more challenging than we anticipated, but we finally managed to get it solved. In the calibration, we can get also sub-millimeter and sub-degree calibration accuracy. And this allows us to move the camera around the target with a sub-millimeter positional accuracy for the path planning for the whole path. And we can guarantee to comply with this threshold of accuracy that we can prescribe. So we can skip the different individual elements. The rail, we had to build a metal frame because otherwise the installation errors, like for example, you turn a screw a little bit more than you should, and suddenly that error amplifies at the tip of the robot arm. So a micro deformation on the rail converts on a few millimeters error. And we want to get an order of magnitude below that. So calibration is very challenging, but again, we are hopefully already past those complications. And we'll be improving in the future with better cameras, and we'll be able to also automate the lighting. So we can automate everything. I'll skip the software side, but we have thousands of lines of code because we had to play with different communication protocols for TCP/IP, Modbus, DMX, NetNet. So real nightmare. We had to use many different languages and libraries and so on. So we've been able to successfully, for preliminary tests, use this laboratory already for replicating orbital inspection scenarios, for rendezvous and docking. So that's a laser. It is the picture that is inclined. The laser is perfectly horizontal, okay? And we had to take away the docking interface because non-disclosure agreement. So the picture is stripped. But we can get reliably rendezvous and docking situations. We've also successfully tested. These results are obtained from a paper by Sergio. Some of the orbit trajectory design algorithms we previously discussed were also based on the work he's doing for his PhD. Magnificent work he's been doing, and it is replicating. Here it goes in steps, but it is, well, long story short, but this the algorithm allows us to do this continuously, and all 6 joints of the robot arm are moving. So we managed to compute the 6 degree of freedom rendezvous trajectory, and then compensate for the relative pose and cancel it eventually. So there are tests that we already performed months ago before we got all the calibration issues right. So, I mean, this is what we'll be hopefully using in the next few months to extend the data sets we are building for the Deimos 1 with laboratory imagery, with our mock-up of the Deimos 1. And when everything's set up, we'll be making these data sets publicly available for all the AI for space community to come join us in this effort to bring these AI algorithms to operationally capable state. And this is all I had. I'm sorry for the few minutes I overrun. And I don't know if we still have time for questions. I can take a few ones if we have, or you can always contact me on my send me an email, and I'd be happy to discuss with you all the doubts you have.
Thanks so much, Hodei. First of all, we are running late, but it was a fantastic presentation, excellent presentation. Yeah, I think we can still, please, for the audience, you can use the chat for questions, and if you want to open any other debate, anything that you want to say, you can just press the raise hand button.
Yeah, there's a couple of hands raised. Before that, I'd like to once more explicitly acknowledge both the project, but especially collaborators and all the people I've been naming in the different slides. And also some of them are present in the seminar. So I'd like to acknowledge their contributions, because I've been more directly or indirectly involved in many of the results I've shown, or none at all. But again, this is done with the work and effort of many collaborators working along with me, and I'm very happy to have them work with me and get things done.
So we have a question by Luis Sanchez asking, do you have any already published work on the 6DOF relative guidance on your research group?
Not yet. The results I showed were for a conference paper we presented in Orlando. Don't remember if it was 1 or 2 years ago. 2024. Differentially flat pseudospectral shape-based solver for embedded MPC for birthing with blah, blah, blah. Sergio did a nice job in developing a shape-based pseudospectral solver. It's called SPOL. It's the one we use for computing trajectories and so on. There's publications coming very soon about that. We have many conference papers about that, so information can be found on that. And no, nothing on journals yet, but coming very soon.
Hopefully. We have also from Luis Sanchez too. Not sure if you are aware of this database and this satellite image generation project. And he's linking one project about deep learning visual space simulation system. I don't know if you were aware of that, Hodei.
No, I wasn't, but I'll make sure I'll check out tonight. Also, I know there's many data sets I'm aware of that I haven't mentioned explicitly in the conference, but because I wanted to, at least for computer rendered images, I wanted to focus on the ones I know closely.
If I can add a note here, you were showing all these renders, and I was thinking on my end on the crazy advances on AI generation, image generation, and video generation. And big laboratories like Google and NVIDIA are building this kind of image generation tools to create training data for robots. And I was thinking like, oh, if some of these AI techniques can be used to enhance these data sets as well. Not only to create, but also to edit images. When you talk about overlaying the Earth and all those things, image edition can be done via a prompt today. So this opens another scale of renders and data set, as long as you have the criteria to say, oh, yes, this is feasible, this is physically meaningful, and it's useful, you as long as you can control hallucinations.
Definitely.
So we also have Jason saying, is there any limitation for optical navigation, specifically on angular velocity of target satellite? And what is the frequency output of optical navigation?
The first question, I get that asked a lot of times. Basically, I cannot give a number, but dynamics in space is slower than most people tend to think. So even for a satellite that's tumbling, rotational speeds are very low. Actually, for operational satellites, if something if a spacecraft is rotating at maybe 1-2 degrees per minute, they already consider that tumbling. So I wouldn't be worried about a lower limit for that for practical purposes. And frequency at which we can operate these navigation algorithms, we don't have numbers on those yet. It's also very hardware specific. So we are hoping to run our models in an NVIDIA Jetson, because they've already been tested in space. They've flown in low Earth orbit. And of course, you can make them run fast in a high specifications computer, but the idea is to find that sweet spot between having a low computationally demanding algorithm that gets the job done. So it's about finding a trade-off.
Can I ask, Hodei, if you go back to the slide of relative pose estimation where you showed the whole pipeline with the different boxes from the input image to the final pose?
Yes.
I know you have so many slides.
Too many, way too many.
Yes, put one. If you
this one maybe.
I'm thinking of all this pipeline. You know how the deep learning minds like mine always try to think on the end-to-end plot problem, if you could have a good 3D reconstruction method like the ones that you were presenting, if you could solve 3D reconstruction from one image, how many of these boxes you could bypass?
I'm assuming you can hopefully bypass all of them. For example, another thing I haven't discussed, because, well, I already discussed a lot. Another NVIDIA algorithm, foundation pose, can take all these blocks into a one-shot algorithm that gets an image. And actually, I'm not fully sure at the moment that it probably can get images regardless of the background and segmentation. Actually, I think so. So it is a one-shot algorithm where you feed it with pictures and it returns the pose, the relative pose. So that's already, you can already do that. The reason we haven't discussed that is because the model is not easy to fine tune. It can be done, but you have to dig deep into the code to be able to do that. So it's not straightforward to fine tune for your own data set, but you can do that. A problem for that is that you not only need to pass the image, but also a 3D model of the image. So it will recognize it and track it. So it does require a 3D model of the image.
Okay.
So if by spacecraft synthesis you get that 3D model, you pass it on, and you already close the pipeline.
Good.
The pipeline with 2 models. Can you do that with one shot?
Yeah.
Probably.
Yeah.
Yes.
But it's
Yes.
pretty neat. Thank you so much. Is there anyone else that wants to comment out anything? Make any other question? Okay, so I think we can wrap up here. Thanks again. Virtual applause to the speaker. Sorry for running a bit late, but well, it's the first one. I think we can allow it. And well, where can people find you if they want to contact you?
Let me show again. Last slide, 156. Wow, that's my email address. So
No TikTok?
just drop me an email. Oh no. No social networks.
Okay.
I do have a few, but I haven't used them in months or years. So no.
So no worries. And so thank you so much again for
My
the rest of the
pleasure.
audience.
Thanks everyone for joining me, and I hope to see you around, as many of you as possible in person soon, hopefully.
So please let me give one farewell message. So we will record. We have been recording this, and we will upload the recording and maybe the slides too, along with the video. And we will publish very soon announcements, and we will share the next speaker, which hopefully will be at the end of October. And we will make the announcement pretty soon. And we hope to see you there, all of you there. Please. Thank you so much. Have a fantastic evening for those of you in Europe, and morning or wherever you are. Bye-bye.
Goodbye, everyone. See you around.
So let's stop recording here.